Thank you for watching Knowledge Academy. Okay, in this video, we will be talking about forces and motion. When we talk about forces, we cannot forget Newton. Newton did some very invaluable work in the field of motion and mechanics. Before Newton, there was a concept force considered as an influence. Right? So people are thinking if something is moving, let's suppose this object is moving, they don't consider this as a force moving this object. They consider this object is moving under influence. Right? And Newton came on board. He did a lot of discoveries, he did a lot of work, and then he discovered any object can move. It must need an efforts, and those efforts called force. These efforts has two types. First one is pull, other one is push. For example, if I have a block, just like I mentioned here, you have two options to pull or push this block. The first one is push. What you can do, you just go here and physically put your hand on this block and try to push it from the back. Another option you have, you can pull this block from the front. And that option is that you can tie maybe a rope or chain something, and then you can just take it out and start pulling. Okay. Now, Newton laws, they are not just one. Newton defined three laws. I'm going to go one by one in a briefly so we can look into that concept in more detail and do some problems. But before we do or talk about the laws, we talk about this push and pull. One thing we have to understand, as harder you pull or push, right? As harder you push and harder you pull, what's happened? The object start accelerating. Accelerating means it moves faster and faster and faster. When things are getting accelerating, it means you start moving faster and faster. Same way, when things start slowing down, we call them de-acceleration. Yeah. Acceleration is represented by A. De-acceleration also represented by A, but they should have a minus sign. It means it's de-accelerating. Okay. If you recall, what is acceleration? Acceleration equals to change of velocity over time. Sometimes you can also write delta t, or you can use acceleration equals to d over dt with the velocity function. Now, if the velocity function is given something, let's suppose velocity is given 5t squared plus 9t plus 2, and you want to calculate the acceleration, all you have to do is just take this velocity and take the derivative with respect to time. Maybe time equals to 2. So first you take the derivative is going to be 10t plus 9, and then you substitute this t value here. So it's going to be look like and it's going to be 29 meter per second squared. The unit of acceleration is meter per second squared. Okay. Now let's talk about Newton laws. Newton provides three laws called laws of motion. Sometimes you call it Newton laws. Okay. Now let's talk about Newton laws. There are the three Newton laws. We're gonna go talk about one by one, all of them. But before we do this thing, we're going to be talking about ideal condition, okay? And then we're going to be talking about real condition. What do you mean by ideal? So Newton laws apply on ideal condition first, and then we can include all the reality inside those laws. So ideal means if I have a block and I want to push this block, or if I want to pull this block, this is what we're learning. Newton says force, apply, push or pull. We can call them force here, force here. The ideal part is that in real life, this block is not free to drag on this surface. They should have a friction. Okay. And this friction force we ignore for now, but it will come back later. Okay. So ideal part is that Newton first says anything is moving. Newton first law. First law says that if any object is moving, let's suppose uh, you throw the rock, right? You throw the rock, or you go to the the bowling court, and uh, you go to the arena and you go to the bowling court, and then basically you throw the ball into the court, and the ball is rolling, right? The ball is rolling, and it's going to be go this way, this way, this way. The ball is moving forward in this direction, right? And then ball is basically moving here and here. What Newton's first law says that it says this ball will never stop, always in motion, unless there is a force applied on it. So if the ball is keep moving in one direction, it will never stop unless and until you apply a force in it. So technically, what speaking, we know that if you throw a ball in real life, this ball is going to keep rolling, and after so many meters, it's going to be eventually stop. But the force acting on the block is really a resistance force which apply against the motion of the ball, and you call it friction. Right? Just like you push your car, and what's going to happen? Your car is rolling, and then you shut off your car. What's happened? The car is keep moving forward for so much, and then eventually it's going to be stopped because the friction between the road and the tires will kill the motion of the car. So Newton laws was valid for all the conditions. So anything is moving is going to keep moving unless and until you apply a resistance or a opposite force. But just like to add over here, one thing is there is a natural phenomena called friction in our life, and friction is the main cause to kill all the motion, right? Because if you think about it, in this universe we have no friction. What's going to happen? You move something, it's going to keep moving forever. It is going to be disaster. If you move the car, you can't apply the brake because there is no friction. Brakes work through friction. So friction is not a bad thing. Sometimes friction is not a good thing, but friction we need it, otherwise we cannot stop things. That is Newton's first law. So Newton's first law really is just a conceptual law. I would say Newton's first law a conceptual law. Okay, it doesn't have any math involved. Let's go to Newton's second law. Which is considered a real law, and there's a lot of work has been done in second law. So Newton's second law, you can call second law. Newton's second law says that if you try to push an object with force, this object is start moving, and what's happened is going to be accelerating. Right? We just learned about it accelerating. If let's suppose you're applying force, maybe force is 10 Newton, it's going to be moved. If you increase the force to 20 Newton, this object is start moving faster and faster and faster. If you do 100 Newton, it's definitely going to be moving much, much faster. Now, more force you apply, much faster this object is moving. Newton says the same thing. He says force directly proportional to more force you apply, more faster you can move the object. It's not only just moving, this is acceleration. It means it keeps changing its speed, I'm using the word getting faster and faster and faster. It means the delta V, which is change in velocities, keep increasing. So the block is stationary, not moving, velocity is 0. You apply 10 Newton, it starts sliding. You apply 20 Newton, it's getting a little bit accelerating, getting start moving much faster. You keep applying more and more force, getting much faster and faster. That is one thing. But the condition is, there's a condition Newton's second law, and the condition is the mass of the block not change. And what does that mean? It means straightforward. It means you applying 10 Newton, right? And after 10 Newton, you say, I'm going to increase the force to 20 Newton. And after you apply the 20 Newton, what you did, you take another bag of sand and putting on the top of this block. So what's happened? This block is supposed to be applying 20 Newton, is supposed to be moving much faster. But it did not because you're adding extra mass. So really what you're doing, you keep increasing force, but you keep increasing mass. So what's happened, this extra mass actually don't let it to move faster. So this law cannot apply in these conditions. This law says, during experiment, do not change this block. Block cannot be changed. It is what it is. You have a car, you're driving your car, make sure your car mass does not change. It means you are sitting in a car, it's fine. All you have to do, just push the gas, push more gas, keep pushing more. What's happened to the car? Car is keep adding velocity and keep moving faster and faster and faster. Okay. So let's complete this law. This law says this: F equals to ma. This mass, m stands for mass, unit is kilogram, a stands for acceleration, unit is meter per second squared. This unit is Newton. So really in real life, if you want to say what is 1 Newton equal to, 1 Newton is actually equal to 1 kilogram meter per second squared. That is a unit of, that's actually, this whole thing equals to Newton. So every time you're writing 100 Newton, is Newton means you're actually writing 100 kilogram meter per second squared. This is what does that mean. Okay. Remember that I just told you we are talking about ideal condition, no friction. Same thing here, no friction means when I push this block, this surface is frictionless. So block is basically sliding, like it doesn't have to be any friction on the ground. Okay. Before we go to Newton's third law, let's talk about this law one more time. People have misunderstood Newton's second law a little bit when say F equals to ma. The complete formula is really like this. The complete formula for this Newton's second law is supposed to be like this. Rather than you writing F equals to ma, you're supposed to be writing this sign and then writing F equals to ma. What does that mean? It means summation. Summation means net. For example, somebody gave you $100. Somebody gave you $100 You gave them back $90, right? So how much gain do you have out of this transaction? You gave them 100, they gave you 100, you gave them 90 back. So really how much you gain? You gain only $10. For example, in this problem, if you try to, you know, um, driving a car, right? Driving a car, and your car is actually pushing forward with the engine, moving forward. You're applying F equals to, maybe I can call F1 equals to 100 Newton force. Since this car is driving into the air, right? There is an aerodynamic, so there is a friction or the air drag. Air actually try to push the car backward, and there is a friction. I can call it F2 equals to 30 Newton. So really, if I want to look into this scenario, I'm going to say this car is moving forward, and this air is trying to push it backward. So I'm going to take this minus this and give you the net, and that is this $10 example. So I'm going to say here 10, 100 minus 30 equals to MA. So I'm going to be using net force here, not like 100 Newton. I have to take 100 minus 30 if there is any opposite force, right? In the same way, let's suppose you're driving a car and somebody is coming from the back, another car or maybe truck. They push you and hit you on the back. The car is actually moving much faster. And this force, the one they got the bad collision, they maybe have 50 Newton. So in that case, what you're gonna write? You're gonna write like F equals to MA. But this is a summation of F. It means all the forces, all the forces. So I'm gonna be writing like this: 100 plus 50 equals to MA, and it's gonna be 150 equals to MA. Yeah, whatever the mass of this car you're going to be using here, whatever the acceleration this car is moving, if you want to calculate, you can calculate. So let's suppose if this car mass is 1000 kilograms, what you're going to do. And if I'm asking, if somebody driving the car, the engine applying 100 Newton, somebody pushed you from the back with 50 Newton, right? There is a aerodynamic force is 30 Newton. What is the acceleration of this car? By Newton's second law, you're going to be apply something like this. You're going to apply like this. So you have three forces: this, this, this. Mass of the car is 1000 kilograms. So I'm going to say is Newton's second law says summation F equals to M. A, M is equals to 100 plus 50 minus 30, because 30 is on the opposite direction, equals to M A. M equals to 1000, so I'm going to be right here 1000, and A is A. And what I'm going to do, I'm going to be just do math over here again one more time. So it's going to be 150 minus 30 is going to be 120,000. A, and A equals to 120 divided by 1000. It's going to be 0.12 meter per second squared. And that is my answer for my acceleration. Okay. Let's talk about Newton's third law. Newton's third law says every action have equal and opposite reaction. What does that mean? It means you have a table, and you have a table. What you did, you just throw the book or drop the book on the top of this table. Definitely book is not massless. Book have a mass and weight. So this book is trying to push downward this table, this table actually tried to push up or have a reaction force up. And if let this force called F1 equals to 18 Newton, this force should be equals to F2 should be equals to 18 Newton. That's the only way this book gonna stay here. If it's not the case, this table is gonna break and book is gonna fall down, or maybe the book start flying. Okay. Another example, Newton's third law. You are driving your car, you park in the driveway, you get inside the house, right? You drive your car, you park in the on the driveway and go to your house. The car is living on the driveway. Now the car is not weightless, car have a weight downward. So car have a weight maybe 1000 times 9.8, so it's going to be 980 Newton, right? And that's the weight of the car. Now since this weight is 9800, what's happened, this weight of the car is going to be distributed on 4 tires. So you're going to be applying, you're going to take this 9800 divided by 4, and whatever the number you come up with, you're going to be apply here, here, on the back tires or on the front back tires. So they have 4 tires, you're going to distribute the load into every tire. But all these forces, like these forces on the reaction and action, so really what does that mean? It means action must be equal to reaction. And that is a Newton. Usually when we learn about Newton's third law, we write it like this. F equals to A, B equals to F, B, A. What does that mean? It means whatever you're applying force on A to B, the force must be applied on from B to A in the opposite direction. Okay. Now, we're going to be talk about one more thing. Maybe you already learned about that one in the past. One phenomena or the concept we call free body diagram. FBD. What does that mean? Free body diagram. Free body diagram is a sketch to make sure all the forces applied on an object must be balanced. Right? Let's suppose I have a system, right? And there is a, there is an elevator, and inside the elevator there is a mass is hanging. This mass also have 2 masses hanging. So I'm going to call M1, M2, M3, something like that. And then the elevator is moving up, and what's happening? I want to analyze every mass. So I want to analyze this mass, I want to analyze this mass, I want to analyze this mass. So what I'm going to do, I'm going to be apply one thing called one at a time. One at a time. And that is actually what does the free body diagram. Like I'm going to take every body in the system and take one at a time. That's what you call free body diagram. What does that mean is, you take a body, let's suppose M2, and cut the M2 from the system and take it out. And how it's going to be look like? It's going to be probably going to be look like this. M2 and M2 have one string attached, so you're going to be attaching here. But you cut it here, so you just say this is a whatever tension. Now this M2 also have a weight, so you're going to be applying the W2. And you're going to be writing this is my free body diagram for W2. Can I apply the same thing on W3? The M3 is going to be same thing, just like M3, and I'm going to be applied W3 and then D, maybe T3, you can call T2. Now if I want to apply the same free body diagram of this mass, which is M1, I'm going to be applied like this. It has two forces. I'm going to call T2 and T3. How do I know? Because you see here I call T2 and the T2 is coming from here. Same thing, T3 is coming from T3 coming from here. Now what I'm going to do, I'm going to be applying one more force. This is on the top. I mean, maybe I can call it T1. Am I done everything? Not really. One thing I missed, and the thing is the weight of this block, right? Like this block have a weight, this block have a weight. How come the M1 doesn't have a weight? It has a weight. I'm going to call it W1. So really you have one force, another force, another force, another force. We have four forces on this guy, which is very hard to see here inside the elevator. So really free body diagram is a phenomenon to analyze different part of the system one at a time. Strategy one at a time. Now what we're going to do, we can also start writing the forces in a vector form. Vector form. For example, if I give you the force, so I'm going to say is force in a vector form. And what does that mean? If I'm applying the force, let's suppose, if I have an object like this, I'm going to push the force equals to 10 Newton. If I want to write this in a vector form, I can write F equals to 10 I. I means x along x-axis. So I have a three vectors. One is x, this one is z, this one is y, maybe sometime this one is x, this one is y. So I'm going to call x-axis along axis I can call I, along y-axis called j, along z-axis called k. So let's suppose if I have an object like this block and you are applying a force, whatever, this way. It's a 3D, right? You applying from this towards you, you're just pushing this block from this corner. Okay, that's much easy to understand. Now, since it's a 3D system, like this way, and this way, so this force is split into three components. So you're going to be writing this force maybe F equals to F x I plus F y j plus F z k. And what does that mean? You're applying the force. I'm going to take the force and split into component. So let's suppose this is my force. It's a 3D force. So I'm going to split into three components. I'm going to call this component along this. I'm going to call maybe Fy dot dot dot. This component I'm going to be called Fx, and the top component I'm going to be called Fc. I just give the number just for understanding. Let's suppose this is whatever component, maybe 100 or 1000 something. These component maybe Fy is 900, Fx equals to 700, right? And Fz equals to maybe 400. Newton, everything is Newton, Newton. Don't take the numbers because maybe the numbers are not right, but I just make up the numbers so we understand. If I want to write this vector again one more time, I'm going to be writing this F equals to, I want to write the component. So first component is I, so it's going to be 700 I plus 900 J plus 400 K, and that is my vector form of my force. Now, things are not always in a one direction. Okay. and sometimes the force in different direction. And that topic, what we're going to introduce, is called forces for an object, force for an object on an inclined plane. And what does that mean? It means, earlier I give the example. I have this table and I put the block here. But what's happened? Now what I'm going to do, I'm going to tilt the table, moving this one here and moving this guy here. I'm going to rotate this table this way. So what is going to be look like, or other way around, this way. So what I'm going to be calling, I'm going to be calling this whole phenomenon inclined plane. Inclined plane. Inclined means something which is an inclined, that is my angle, theta. And I'm going to be putting the object here, so my object may be here. This object have a mass m. So now the thing is very important. We have to understand that since I used to have my x and y axis like this. Now I tilt this surface, right? I make the surface and tilt it or rotate it. So my surface now is on this direction. So what I'm going to do, I'm going to be making my x-axis maybe here, right? And my y-axis I'm going to be making here. I'm going to name these axes. I'm going to call maybe x, this one, and this is one y. All you did just taking same this axis, and then where this is y, this is x, you just rotate it. So x is going to be going here, and then y is going to be going here. Now think about it. Now let's take a look on this mass. What is going to happen? This mass weight is downward. If you put the mass here, its weight is also down. Weight always downward, regardless of orientation of the plane. Doesn't matter how much you rotate. This is weight, this is weight. Now this weight, the one I'm just drawing here, is going to be two component. So what I'm going to do, I'm going to call this weight some naming. So I'm going to call this weight maybe FG. So FG is my force due to gravity. And basically that is called weight. The definition of weight is this: force due to gravity. Now this force is going to be split. Since every time the force is not along x or y axis, I can split the force into here and here. I can split the force. I can split the force. So this force I can split in here, along this axis and along that axis. Let's split it and see how it is going to be like. So what I'm going to do, I'm going to take maybe green color, maybe white color. And I'm going to say some of the force of this one, I'm going to make the perpendicular here. And I'm also making the perpendicular on x and both x and y axis. So this guy you're going to be saying x-axis, this one you're going to be called f g x, and this side you're going to be called f g y. Fg is the force of gravity. It has two components, fgx, fgy. We know that if you have scenario like this, you have a force. I'm going to be drawing here one more time. If you have a force like this, you can just split the force, and this angle is also theta. This angle is theta, this angle is also theta. So if you want to write the formula for this, You're going to be writing like this. We just call F1 again, F call F G X equal to F G sine theta, and this one is F G cos theta. Okay. Now what I'm going to do in this case, I need to apply Newton's third law. Newton's third law says every action have a reaction. Every action have a reaction. So what Newton's third law says, every action have a reaction. I'm going to take this legend arrow, and every action have a reaction I'm putting over here, right? And basically this is my reaction. The magenta is reaction, right? So I'm gonna, maybe I can just maybe I can name something. Maybe I can call it normal force, Fn. So Fg is a force of action, Fn is normal reaction force applied by the plane. Okay, so now I have two things going on. I have a motion along x-axis and motion along y-axis. I'm going to be applying Newton's second law on x-axis, and my force must be equal to the balance, whatever the force. I'm going to be same thing applying Newton's second law along y-axis, and my forces should be equal to 0. So in this case, I'm going to be applying the Newton first law along x-axis. So I'm going to be writing how many forces do we have along x-axis? Really, I have just this force. There's nothing else along x-axis. It's only this. Along y-axis, how many forces do we have? I have this force, and I have that force. So along y-axis, I'm going to writing like this. I'm going to say, F. The total force applied in the x-axis should be Fg sine theta, and that is the force I'm applying along Fx. Right. The y-axis, I'm going to be applying the second law is going to be look like Fn. Why do I say Fn first? Because Fn is positive, because it's upward. So every force here is positive, every force here is negative. Right. Same thing, if you want to do the other force, you can also write here a negative sign. It means this force towards the negative f-axis. So this x-axis towards negative sign will be considered negative. Here I'm going to be writing Fn minus Fgy cos theta should be. And I can consider that Fn should be equals to Fgy cos theta. Okay. Now this Fx is considered as to be Fgx. So really, if you pay attention in this problem, this is the force who's bringing or sliding. This block is sliding, right? This block is going to be slide downward. So who's bringing this block down? This force. And what's happening? This block is not moving here in this way. So what we're going to do? We says that here, we're gonna call Newton's second law says F equals to M A N A. One says M A X and M A Y. Now, since this block only, so this is an inclined plane, block only move this way or that way. Block cannot go up or down. So block cannot move this direction. So really, this whole thing will be 0. That's why I'm substituting here 0, right? And when you multiply the m with 0, so it's going to be m times 0. So really, if you want to write one more time, you probably can write like this. M 0, because ay is 0 block cannot be moved along y-axis. However, I cannot write like this. I can rewrite this guy a little bit better. And I want to say is only one force F equals Fg along x-axis is going to be equal to this. And I can write like MAX. And from here, if you want to calculate AX, or it's better to just say is acceleration just A, you can write Fg sine theta over M. And that is my expression. Yeah. I hope this understand Newton's laws, their implication, their application. We will be doing some problems to understand them better. Let's take a look at another problem. Yep. So we already draw F1, F2, and F3. In this problem, we're going to be applying Newton's second law. But before than that, we have to understand how we're going to apply Newton's second law. So we have three forces. F2 along x-axis, so I'm going to be drawing here. F2 is along x-axis. F3 is not along x-axis. It's going to be split, right? So it has one component. I can call maybe this component is F3x. Same thing, I have another component for F1. So F1 also have another component. Maybe I can call another component here. So there's a 3 vector. We can draw maybe red color vector, so you know that. One here, one here, one here. So this one I'm going to call F1x because this is F1. The other one is F3x and the other one is F2. And all the angles are given. If you can pay attention here, F1 is given, F2 is given, F3 is given, theta 1 is given, theta 3 is given. There will be no theta 2 because theta 2 will be 0 in this case. So what I'm going to do, I'm going to be writing here net force apply on the system along x-axis. Okay, so I'm going to be saying F net equals to F1 plus F2 plus F3. That is my net force. And Newton's second law says F net equals to MA. So what I'm going to do, I'm going to take this M net, substitute the value. Is going to be A equals to 1 plus F2 plus F3 divided by M. In part A, they're asking in a unit vector notation, we need to find out what is the astronaut acceleration in a unit vector notation. Right? So the notations of unit, the notation of the vector should be in unit vector form. So what I need to write all F1, F2, F3 in a notation form. So I'm going to be writing here F1 equals to F1 cos theta plus F1 sin theta. So F1 cos theta plus F1 sin theta. And this one should be I, this one should be J. Okay. I can write like this. I can say is 32, which is given in the problem, cosine 30, which is also given in the problem, and then I plus sine 30 degrees J. If I solve it, you can do it. cosine 30, I think 0.866 times 32, the answer would be 27.7 Newton I. So we're going to take this and multiply the cosine 30 values 0.866 times this, so that we get an answer. Sine 30, I think the value is 0.5. You're going to multiply by 32. The answer would be half of it, which is 16 Newton J. Keep in mind, this is just F1. We need to do F2. F2 is along x-axis, so there will be no y component. So I can write this just in case, so we understand better how it happened. I'm going to write cos 0 because that's F2 is making a 0-degree angle with x-axis. You can see here is along x-axis, plus sine 0 j. Sine and cosine, when you do it, I think sine 0 will be 0, cosine 0 will be 1, so answer will be 55 I. Right. Same thing with F3. I'm going to be writing real quick, cosine minus 60 I plus sine minus 60 j. Right. And the reason is minus 60 because you can see here, this is a usually we measure the angles from positive this direction, but F3 direction is giving this way. That's why we're using minus 60. The problem is giving 60, but we're using minus sign because it's a negative direction. It's like clockwise. We usually measure the angle anti-clockwise from positive x-axis, which is this way or this way, whatever ways it's going to come. Right? Let's substitute the value. It's going to be 20.5 Newton I plus, sorry, minus 35.5 Newton J. So we got all the forces in a vector notation. What we can do, just taking equation number 1, 2, and 3, and substitute in our equation A. Okay, so we're going to substitute into A and see how does it go. So we're going to be continue this problem and substituting the value 1, 2, 3 in equation A. So A is going to be look like this: 27.79 plus 16j. I'm going to take the values from F1 plus F2 plus F3. It should be minus. So I'm going to take all the i's and add them together, and then adding all the j's together and divided by 120, which is given in the mass in this problem. So all I can do, I can add them together and then divide. So my answer would be 0.86 meter per second, which is I. I'm going to add this to this to this, and whatever I'm gonna get divided by 120. This is my answer. Same thing. What I'm gonna do, I'm gonna take all the j's and add them together. Some of them are minus, so really I'm gonna take this guy, add minus 35.5. The answer should be negative, and this is what we got, and then divided by 120. So the answer is minus 0.16 meter per second. Don't forget to write in J. And that is your acceleration in the vector notation. In part B, they're asking the angle of this acceleration, right? The magnitude. This is part A. Done. Part B, they're asking A magnitude. And magnitude equals to, vector magnitude equals to ax squared plus ay squared. So really in this problem, this is my ax, this is my ay. I'm going to substitute the value equal to 0.86 squared plus minus 0.16. And if you add them together, the answer will be 0.88 meter per second squared. Part C, they're asking the direction. Is going to be tan theta ay over ax. Ay is here, ax here. Let's substitute the values and you're going to get the answer. So theta equals to tan inverse. So what we did, we just take this tan theta, tan on the other side, leave the theta here, and tan becomes tan inverse. And ay is minus 0.16 and ax is 0.86. We solve this, the theta will be equals to minus 11 degrees. These are our answers. Let's take a look at another problem. In this problem, a block of a weight 3 Newton is rest on a horizontal surface. A 1 Newton upward force is applied to the block by means of an attached vertical string. What is the magnitude? A. B. The direction of the force on the block on the horizontal direction. So what exactly happening here? A block of weight 30 Newton. So there is a 3 vertical forces acting on a block. The earth pull, which is the weight of the gravity, right? So I'm going to take the block. Is rest on a horizontal surface. So this block is weighed downward. So how much is given 3 Newton, which is given in the problem. Rest on a horizontal surface. A 1 Newton upward force applied to the block by means of attached string. So really what's happening, you're applying a upward force, which is only 1 Newton. We need to find the magnitude. What is the magnitude and direction of the force on the block, the horizontal surface? So let's think about it. For a minute, just a minute, we can assume there is no string attached. Newton says every action have a reaction. So if you try to, or this block, try to push this floor downward, this floor try to push it up with the same force. Now what you did, really, you take an extra string, you connect it here and start pulling it up, called 1 Newton force. So this 1 Newton actually reduce the reaction because now out of this 3 Newton, you are applying 1 Newton. So how much is left? 3 minus 1 is equal to 2. So only 2 Newton force is going to be applied on this block, on this direction, on this face, right? What we're going to do, we're going to just draw that force. So we can draw here. Maybe we can just say a string attached is pulling force equals to 1 Newton. We're going to come here and apply Newton's second law along y-axis. Right? Along y-axis, I'm going to be applying, and my resultant should be equal to 0. So what I'm going to do, I'm going to apply like this. Since this block is not moving, it's just sitting on the floor, even though you're applying the forces, this guy has become 0 because not moving. So basically, all the forces summation along y-axis should be equal to 0. Let's apply. So how many forces do we apply on this block? We have 3 forces applied. Let me draw a free body diagram. So I have a downward weight, 3 Newton, upward force of 1 Newton, and I have another force which is called Fn, normal force. So if I'm going to apply Newton's second law here, it's going to be equal to Fn, which should be positive, plus 1 minus 3 equal to 0. 3 Newton minus 1 Newton minus 1 Newton because it's downward should be negative. So if I do my math, I'm going to get Fn equal to 3 minus 1. The answer of Fn is 2 Newton. Where? Upward. Right? Now in this problem, if you pay attention, it's saying here, B part, direction, we need to find out of the force of the block on the horizontal surface. So really we need to find out how much horizontal force block apply on the floor. So really this is the Fn. So I'm going to say that this block applied 2 Newton downward force. Right? This is Fn means up one, and the left over is 2. Let's take a look at another problem. Look on this problem. It's a little bit complicated problem, look like, but if you pay attention, we're going to follow the discipline. We already talked about this mechanism, how we can split the forces. In this block, that's the mass of the block, the 8.5 kilogram, and the angle is 30 degrees. So 30-degree angle given, mass is given. Find the tension in the core. We need to find the tension in this core. B, the normal force acting on the block, the normal force acting on the block. C, if the core is cut, find the magnitude of the resultant acceleration. So if let's suppose we're going to cut this cord or this string, the block starts sliding down, we need to find the acceleration. So what I'm going to do first thing, I'm going to be saying here solution. Since this problem needs a very detailed free body diagram, so I'm going to be writing here free body diagram. Make sure I'm going to be writing a very clear or drawing very clear free body diagram. Block here will look like much steeper than what I draw. So I'm going to be drawing a block like this. In free body diagram, you mostly just draw the forces. So I have a bunch of forces. The first one is tension in the string. I'm going to call it T. Another thing is the weight of the block, which is W equals to mg, which is given in the problem, by the way. Other thing is that you have one force. This force has two components. One component of this force is along this axis, and one component is along this axis. This one I'm going to be calling mg. By the way, this angle is theta, this angle is theta, which is 30 degrees given. mg sine theta. This one mg cos theta. We need one more force which is supposed to be on the top, and we can call F n. Okay. Since we have two axes here, one is this way, one is this way, I'm going to call this is x, this is y. So what I'm going to do, I'm going to apply the Newton's second law along x-axis. So apply second law along x and y axis. Okay, one by one, let's apply. So if I apply along x-axis, since block is not moving, it's hanging there, my total force should be equal to 0 because a should be equal to 0. Block is not moving. I'm going to write in T positive. So T along x-axis, here's a T force. The other force will be negative, which is my mg sine theta. So I'm going to write in minus mg sine theta equals to 0. Along y-axis, I have one force called Fn. I have another force called mg cos theta, which is right click. I'm going to write this one just like we wrote on the free body diagram. I'm going to write here where T is the tension in the port and Fn is the normal. We have two parameters. We are using T and Fn. Make sure we elaborate them. In A, we need to find out the tension of the core. Okay. In A part, we need to find the tension in the core. So I'm going to say A. From here, I'm going to say is T equals to. I'm going to take the mg on the other side. So it's going to be mg sine theta. From here, I'm going to just substitute the values. T equals to 8.5, 9.8 sine 30. So my tension comes out to be 42. Part B, the normal force acting on the block. So I'm going to say is from equation 2, Fn equals to, I'm going to take the mg cosine theta on the other side. So it's going to be mg sine theta. Substitute the values. 8.5, 9.8 cosine 30. Fn equals to 72 Newton. This is also Newton. That is my answer for part. Part C saying if the cord is being cut, the cord is being cut, like the string is being cut from here. What's happened when the string is cut? The T becomes 0. The T will be gone, right? T will be gone. When T will be gone, it means the block actually sliding downward. And there is no T here. There is no T here. Only one force applying downward, which is this force. Okay. So let's take a look what we can do. In part C, I'm going to be writing same equation. Maybe I can just write a block here. This guy is moving down in C. There is no force. I have Fm. We have W or mg cos theta. This one is mg sine. Since this block is sliding downward, really, it does not move along this way. So this force and this force are balanced. So really, I'm not going to be talking about forces along x-axis, y-axis. I'm going to be talking about forces along x-axis, which is only this force left. So I'm going to be writing here when block slides downward and t is gone, so t equals to 0. My equation, this equation is going to look like this. It's going to look like mg from here, right? For this equation, fn summation fx equals to, let me just write completely. So along x-axis, I'm going to be writing f equals to m a. I want to calculate a. Before we do, I'm going to be writing summation of forces along x-axis. So there is only one force in x-axis, which is mg sine theta. If we are lucky, is only one force, but it's negative because it's moving down. See, this is negative sign because it's going towards this direction. It should be negative, so negative equals to m a. This m and this m cancelling out, so a equals to minus 9.8, which is g sine 30. And from here, if I calculate the a, is going to be minus 4.9 meter per second squared. That is my answer. This minus sign telling me my acceleration towards negative x direction. Let's take a look at another problem. In this problem, we are looking into a scenario in vertical direction. So an elevator, cab, and its load with the combined mass of 1600 kg. Find the tension in the supporting cable when the elevator or the cab originally moving downward at 12 meters per second is brought to rest with constant acceleration in the distance of 42 meters. So maybe there is a mass over here, right? It's coming down, and the mass is given 1600 kilogram. When you start making it slow down, it's going to be t. How much distance is going to be traveled? It's going to be traveled some distance. And at this point, when the cab is going to come here, the velocity equals to 0 meter per second because it's completely stopped. 42 meter is the distance traveled. Okay. We can apply Newton's second law along y-axis. So in this cable, we also have the cab is connected to the top, so it's going to be tension, right? And this is a weight. It's going to be downward, mg. I'm going to apply along y-axis. Is going to be t minus mg. Since this is a moving system, I cannot say equals to 0. It's going to be m a. Okay, where a is acceleration in this case for the cab or for the elevator box. From here, I can say tension. In this case, I need to find out tension equals to mg plus ma maybe I can simplify it a little bit. I'm going to call m is a common g plus a. This cap is going to be moving downward with a velocity of 12 meter per second. So this is my initial velocity. Maybe I can call vi. This is my final velocity. You can call vf. Vf is 0 because my elevator is stopped. So maybe I can apply Newton equations of motion, and it's going to be applied like this. We need to find the acceleration, so we're going to say from equation of motion, there's a 3 equation of motion. We're going to choose one of them. So we have vi equals to minus 12, vf equals to 0, and obviously is meter per second. That's the standard unit. We're going to apply this equation, and the equation is v squared vi squared plus 2a delta, whatever the delta x. Here is the distance is y. So this is my distance, y is the distance. So what I'm going to do, I'm going to be substituting the value. Really, this guy is 0. So I'm going to rephrase this equation. I'm going to write like this. 0 equals to minus 16 squared. I think it's 12. Yeah, 12 meter per second squared. And minus plus, and it's going to be 2 a y. Here is the y is negative, so I'm going to say it's 42 with negative sign. Towards downward is negative. If I want to get I want the a out of this, so I'm going to say is a equals to minus 12 meter per second squared or minus into, I'm going to say is minus 42. If I solve my answer would be minus, it should be a minus getting plus, right? And there is a minus here. It's minus getting plus. Going to be 1.71 meter per second. Okay. So we need to find the tension in the string from equation 1, which is this. We're going to say T equals to ma plus g, and everything pretty much is given right now. The mass is given 1600, g is 9.8, and a we calculated 7.71. If I do this one, the tension equals to 1.8 exponent 4, and tension is a force, so there should be Newton. Thank you for watching Knowledge Academy. Please subscribe my channel.